Hi, thank you so much for joining us this evening. Today, we're going to be going over a simple data set with some pretty complex results. Today, it's going to be talking about car data, specifically customers that have purchased a car in the last year, split between gender, annual income, as well as age. Our project group is myself, Robert Blue. I'll be going over the exploratory data analysis. Jasmine O'Neill will be taking care of Objective 1, which is a simple interpretable model, as well as Vo Nguyen, who's taking over Objective 2 and the conclusion, which is a more complex, a little bit more interactive model, as well as the non-parametric models. And then he'll be wrapping everything up. The next few slides we'll go over is going to be our exploratory data analysis that we were able to actually dive into. As I said, our team was tasked with finding out if basic customer attributes can be used in effectively predicting car purchases. Our data set is pretty simple, but we were actually able to find some pretty interesting results from it. We've been provided some basic customer data through a car dealership, whether or not they're able to purchase a car, yes or no. We use different statistical models such as logistic regression and some different classification models, as well as non-parametric models to determine the prediction. Through our EDA, what we found was that the data set was pretty small, at first glance at least. There were only 4 variables that were included for predictors and only 1 response, of course, for the purchase. With these variable limitations, of course, that means it opens up some ways for creative ways to explore the data. So what we did was that we actually looked at the age and the salary ranges, and we created some demographics and groupings from both of those groups. These groups allowed a deeper analytics and kind of uncovered some things that were not so obvious from first glance. As I said, so the data is 1,000 observations. But there's only 3 predictor variables, such as age, annual salary, and gender, and there's only 1 response variable. There is a user ID, but we didn't include that within because it's just a classification of the customer and didn't have any bearing on the actual purchase. So let's look at some of the big picture tickets. As we said, the variables in black are the original ones. We have our gender, age, annual salary, and purchased. But then we added 3 new ones. We had our salary range, our age range, and our purchase cat. The salary range and age range were made as factor just because that was something that we can do to actually factorize it and create the groups to look at. Everything else is numeric, and then we changed gender from a character icon or character variable to a factor variable. Again, this helps with our analytics. Some interesting stats. So it was pretty split evenly between gender, 516 males versus 484 females, and this will come into play. The age range is as young as 18 to as old as 63. The annual salary range was from 15,000 to 152,500. So a pretty eclectic view and very, very wide view of socioeconomic statuses. The purchase, I looked into this and it was actually pretty interesting because the mean was 0.402, which means that there was a 40% no rate. So for out of 100 customers, 40 would say no, which was pretty interesting. It's a little bit worse than a coin flip. And of course, what we wanted to do is provide our customer with a way to up that no rate, or sorry, lower that no rate and increase the yes rate. And through that, we were actually able to explore some demographics and potential ways that they can increase their marketing. So what I wanted to do here is actually I wanted to kind of give a bigger idea and a more clear picture of what our data looked like. So I split the data between your yeses and nos, which is what you see on your left. That's just your count of purchases. Again, we have 598 people who said no and 402 who said yes, which gives about a 40% rate of success, give or take. If we split it by gender, the percentage of females versus males is actually slightly higher percentage of females according to our data set versus males, but we'll go into a little bit more with our modeling. As I said before, we also had our age distribution and the percentage weights of our age. It's a pretty wide distribution, but it's actually normally distributed, it looks like, between the ages about 35 to 45 that make up the majority of it, with some peaks here and there amongst your younger and your older crowd. But if you look at your purchase percentage, it is heavily in favor of, you're heavily skewed towards your older crowd. So your 45 plus crowd actually tended to buy a car more than your younger crowd, with ages of between 18 and what looked like 22, virtually zero people bought a car at that age. Did the same thing with our annual salary. Pretty widely distributed, but it's a pretty normal distribution with a majority of around the 70,000 to 85,000 range. With both of these findings, what we did is we actually ended up grouping up both the age and the salary into different groups. So first, what we did is we took the age range. We wanted to split into 5 different categories, basically to represent the different demographics and different generations. So we did 18 to 24, 25 to 34, 35 to 44, 45 to 50, and then older than 50. This provided some pretty interesting analytics and pretty interesting views from what we actually saw. If you look at the counts, again, split by yes or no, whether or not it was purchased or not, as we saw in the previous graph, it's pretty heavily skewed towards that higher age. So 45 to 50 and greater than 50. It's the majority of them actually were the ones that purchased it, and actually you can see this a little bit clearer in the percentage below. So over 75% of 45 to 50 walked out with the new car, whereas almost 90% of your older than 50 crowd walked out with a new car if they walked in. 0% of your 18 to 24. So not a single demographic of that age bought a new car. We wanted to do the same thing with the salary range. So again, we split into 5 different groups that represented different socioeconomic statuses. And just like with the age ranges, I wanted to see what our actual percent count and purchase count for each of these groups are. What is surprising is that the percentage of 40,000 to 70,000, 70,000 and 97,500, very low percentage of people who actually walked out with a new car, whereas the opposite of your higher earners, so your 97,000 plus, like I said, over 75% of them. And in the case of 100 more, or greater than 120,000, almost 90, if not more than 90%, walked out with a new car. And then we kind of wanted to give a little bit more of a deeper dive. This way we can actually split both of those groups, both the age range groups and the salary range groups, by gender to see if that had a factor into it. And what we saw is quite a bit of the same, but we were actually able to look into the analytics that your female group between your age groups were more likely to buy a car versus your male groups. And then same thing with the salary range is actually, it's pretty evenly spread. But again, you're looking at those higher salary earners more likely to buy a car. And the same thing with your age range. Your higher age range tended to actually buy a car with the females, whereas it's actually pretty evenly distributed and pretty even across the board between your 35 plus for the male group. Now we wanted to look in your percentage, your purchase percent by age, and this again we split it by gender. This time we just looked at raw age instead of the age groups. So again, from our graph, this is not really anything surprising. Just your percentage as you get older, as the older crowd, you tend to buy more cars. That's what we were looking at here. The female group tended to be a little bit higher on the baseline, whereas the male group, the higher the age, you actually had a higher chance than the female group. And then we did the same thing for salary. Now, what is interesting about this graph is that big dip in the middle with that upswing. So it looks almost like a parametric or quadratic equation. But the thing is that if you notice where that dip is, there is a good chunk of data that is missing from both the female and the male for the yeses. Whether or not that means that it is centered solely around the no's, or there's more no's, or there's just not enough yeses on that data, but we were actually able to explore this a little bit in our modeling. Finally, what we wanted to do is we wanted to look at a scatter plot, again, to see what kind of clustering we have, if there's any kind of, if we can use either a k-means clustering, or see if we can do a potential LDA or QDA. And what we found is that it is pretty good clustering that is indicative of a QDA model. We don't have a good linear separation, but we have really good quadratic separation. And this graph, you can actually see it's a pretty good boundary. This is just a rough sketch of what we saw, and the same thing with the males. It's a pretty good quadratic boundary. So as you can see, we actually were able to extract quite a bit of information, even from just those three variables. So with those findings, we were actually able to build some very robust modeling and actually dive into it. In fact, let me hand it over to my partner Jasmine, who can explain the base modeling that we were actually able to find from this data.
All right, thank you, Blue. So now we've had a chance to review the EDA to get a better sense of our data and to have a better understanding of the relationships that we should use when it comes to building out our different predictive models and ultimately assessing the performance and purchasing cars. Now we'll get into objective one, which is to build our base logistic regression model. And so below here we have our ideas that we took in the approach we took to build this model. So essentially we wanted to establish a baseline for understanding the relationships between the predictive variables and the response variable. So we want this to be very simplistic and intuitive based off of that. Given that we have limited variables, it just makes sense for us to go ahead and include that in this base model, considering that these are customer attributes that could have some sort of impact on customers' decision to purchase cars. So we wanted to look at if there were any multi-collinearity issues. So we looked at that via the variance inflation factor. And as you can see from the output here, there were no multi-collinearity issues. And so as a result, we included these variables in our base logistic regression model. Okay, so in this slide, you can see the output from our base logistic regression model. So on the top left, you can see that we use gender, age, annual salary as our predictors and trying to predict the outcome of purchasing cars. And so you can see the coefficients and the estimates for those. And then just below that, you have the confidence intervals for each of those coefficients. And then to the right here, you have the interpretation of each of those coefficients. And so looking at the first coefficient here, we have gender male, which is just looking at the gender male and female and looking at their impact on purchasing cars. And so looking at the interpretation, holding other variables constant, it's estimated that cars purchased by males is 0.32 higher than that of females. The 95% confidence interval for cars purchased by males is contained in the interval negative 0.04 to 0.68. And then for age, for a 1 unit increase in age, car purchases increased by 0.22. The 95% confidence interval for cars purchased is contained in the interval 0.19 to 0.25. And then annual salary, just from a quick glimpse here, you can see that's a pretty small number. And so just to kind of give you some insight into our complex modeling, we'll hope to improve upon the accuracy of these estimates as well as the interpretation of each of these. So looking at the practical and statistical significance of each of these coefficients, we'll look at each of these coefficients. So for the gender male coefficient, statistically from our base model, it was deemed insignificant. But from our practical side, I think we can assume that gender does have some sort of practical significance, though it was deemed statistically insignificant from our analysis. So this just may be due to our limited data set. But I'm sure with a more robust data set and with more robust modeling, this can definitely have some sort of impact. And looking at the age, this was deemed statistically significant. And then just looking at the practical significance of this, I think it just makes more sense that, purchasing power of individuals improves with age. So for instance, young adults, they begin their careers and they eventually become established and start families. So basically, having an income that can support them to be able to, purchase vehicles for their families and whatnot. And then older adults, they accumulate wealth over time. So both of these scenarios reflect the demographics of those that are most likely to purchase cars. And then looking at annual salary, again, it's safe to assume that, with a higher annual salary, you're more likely to purchase a car or have the ability to purchase a car, but it's still up to the individual buyer on if they actually are in the market to buy a car. So that's still a decision that's up to the consumer. And then from a statistical standpoint, annual salary was deemed significant. So in this slide, we're just looking at the odds ratio based on our base model. So the odds ratio for gender male, the odds of a male purchasing a car is 1.37 times higher than that of a female. And then for age, the odds of purchasing a car increased by a factor of 1.25. And then annual salary, the odds of purchasing a car increased by a factor of 1.0. So in this slide, we're looking at the effects plot based off of our base model. So in this, we're looking at the predicted probabilities of purchasing based on a combination of different variables. So in the image to the left, you can see that we're looking at the combination of age and gender. And based on this graph, you can see that at a younger age, in your early 20s to 30s, it's pretty close in line with females and males having similar purchase probabilities. But then as you get older in age, there's a little bit of a gap. So it shows that males tend to have a higher purchasing probability compared to women. And then as they get older in age, then that gap kind of closes. And then to the right, we have the predicted probabilities based off of gender. And again, this kind of shows the differences between males and females, with males have a higher predicted probability of purchasing compared to women. And so in this slide here, we have the model diagnostics and metrics. So just looking at the performance of this base model based on the predictors that we have. And so looking at the AIC of 750.95, this is decent, but we definitely want to explore how we can improve upon this number with more complex modeling. So we'll get into that with objective 2. And then to the right of that, we have the confusion matrix, which is looking at the accuracy of predicting the purchase outcome. So in this case, we achieved an 80% accuracy rate. And then for sensitivity, we were able to achieve 0.94, that's looking at the true positives. And then for specificity, 0.60, positive prediction value is at 0.77, then negative predictive value is at 0.89. So these are pretty decent numbers, but again, we'll definitely look to improve upon this with more complex modeling. And so with that, I'll hand it over to Vo to get into objective 2.
Thank you, Jasmine. Hi, my name is Vo. I will be presenting objective 2, which is going to be more on building the complex models and using different models such as GLMNET, QDA, and KNN. So I'm going to go ahead and explain an approach of what I'm doing, a quick summary. And so our first little bit, we're going to create a complex multiple logistic model by first adding and removing predictors based on the AIC. And we're going to explain why we're using the AIC. The AIC is used because we only have 3 predictors. And so I'll explain more about that in the next slide. After we're adding and removing certain predictors, we're going to go ahead and add interaction terms based on the deviance test, AIC, and the EDA analysis. After we finish including the interaction terms, we're going to talk about the log terms, which we will not be able to add based on the AIC, and we'll talk more about that. And lastly, we're going to go ahead and try to add polynomial terms, which is going to be a quadratic polynomial term based on the low S-plots. And then finally, we're going to compare everything using a Hausdorff test. Now, our second way, procedure we're going to do is use a feature selection model on our complex multiple logistic model. We're going to have multiple predictors from our complex models, such as the new predictors, the interaction terms, and the polynomial terms. With multiple predictors, we're allowed to use the feature selection to choose which one can stay and which one can leave, based on the metric log loss. And now, the other 2 models we're going to primarily use is the QDA, and QDA and the K-nearest neighbors can be based on our EDA analysis of predicted probabilities of annual salary versus age. And you're going to see like boundaries that we can draw that can use those 2 models. Then lastly, we're going to end up comparing everything and seeing which one is going to be our final model based on the AU-ROC. Okay, so now we're going to talk about the metrics. So here are the metrics we're going to talk about. Primarily first is the AIC. AIC is sometimes not trustworthy enough. This should be taken not as serious as the other metrics, but in our case, since we only have 3 predictors, it doesn't really help us if we're going to use feature selection log loss, because there's not much feature selection we can do. But we can use AIC to determine which one is the best out of those 3 predictors in terms of adding interactions of polynomial terms. Our main metric we're going to use for our models is going to be log loss when we're training our data set. And our main primary metric we're going to focus on comparing the final models is going to be the AROC. And lastly, our secondary metric is going to be the fusion matrix. It's going to provide insights and secondary validation of which model is the best. So that's going to be sensitivity, which is going to talk more about proportion of true positive correctly identified, specificity, proportion of true negatives correctly identified, our PPV, proportion of true positives among positive predictions, NPV, proportion of true negatives among negative predictions. Okay, so let's go ahead and start cooking, making our complex multiple logistic model. So we have 3 different models we're going to try in terms of adding and removing predictors. Our very first base model that Jasmine covered is going to be the one categorical variable and 2 continuous variable, which is gender, age, and annual salary. That AIC gave us about 750, and they had low VIFs. Now, what we're going to try based on Blue's EDA analysis of separating the age and annual salary into different bins or buckets, calling them age range and salary range, we're going to make a model based on those predictors of all categorical variables. When we did that, that gave us AIC about 624, and those VIFs are still low, which is a good thing. Now, our team decided that we should combine both the base model and the categorical model into one model, and we're going to call it a simple model by adding the gender, age, annual salary, age range, and salary range. That gave us a very low AIC of 605, and the VIFs are still a little bit higher, but not too high. It's still under 5, which means that we still have low multicollinearity. Now, our next step here is after we're adding or removing predictors, we're going to see if there's any interactions going on. So based on the AIC and the deviance test. So our interaction model 1, what we did here is that we're going to go ahead and take our categorical variables and make them interact with gender based on our EDA analysis. On the AIC we got was 617, but it failed to reject the null hypothesis for the deviance test, meaning that those interaction terms are not significant. And so now we're going to go ahead and go to interaction model 2, which talks more about the different, we went ahead and separated all the different interaction models together. And then we make sure to have age range multiplied by gender, salary range multiplied by gender, age and times gender, annual salary times gender. And that gave us an AIC of 596. And we continue to have a good deviance test where we rejected null hypothesis, meaning that at least one of the terms is not 0 or is significant. And lastly, interaction model 3 has all the interactions, and that gave us an AIC of 500, and it rejected null hypothesis 2 for the deviance test. So we went ahead and kept interaction model 2 just for the sake of not including those interactions, which was between age times age range, which interaction model 3 had, as well as annual salary times salary range. We felt like those were unnecessary predictors that would affect our model and have a harder time interpreting. So we went ahead and included just those two models. I know that in interaction 1, that those interaction terms such as age range times gender, salary range times gender seem insignificant because they failed a deviance test. We still went ahead and just add them to interaction model 2 because in our EDA analysis, which I'm about to talk about, kind of justified those interaction models or interaction terms. And so here we look at age range times gender, salary range times gender. There's a lot of things that we have to uncover based on the EDA analysis from Blue and Jasmine. If you look here on the far left, age range times gender, you see that there is a lot of good stuff that happens here. Starting from the bucket of 18 through 24, everybody's going to buy a car, male and female, which makes sense because around 18 to 24, most people are starting to drive, most people are starting to get the first job, most people are starting to work in order to get their car first. Usually people get car before they get a house, which makes sense in the first bucket. And as you move towards your age, males tend to buy cars more than females, which that makes sense to our EDA analysis and our base model interpretation, meaning that males are more likely to buy cars than females. If you look as they grow in age, from 25 all the way to 44, you see that males buy more cars than females, but then it drops, it switches from females to males, which is interesting because we don't know what's going on there, but then it switches back to male than female, which kind of shows you like, hey, there's some sort of interaction going on between your age range and your gender. That continues in the second predicted probability effects plot, which shows that females are slowly getting up there in terms of buying more cars based on their annual salary. If they have a higher salary, they're more likely to buy a car. So there's some sort of annual, we're seeing like kind of like opposing thoughts, but we're not going to really sure we're going to interact annual salary with gender. Now on the far right, salary range times gender. So those two ideas are almost exactly like each other, but they tell somewhat of a different story. Salary range times gender, we see that here in the same situation. If you are in the salary range right here between 18 and 24, you're more likely going to buy a car. It's your first thing to do. As you move up in age, your salary moves up. And it's kind of interesting because at the lower salary, you're more likely to buy a car if you're male. And once you go up in your salary ranges, at the bucket between 25 and 34, at the top end of 34, you're more likely as a male to buy a car at a higher annual salary range. So that makes sense because, you know, most of the time when, for most folks, typical American if you're becoming more successful in terms of your career and you're gaining more salary, your first kind of situation is buying a really nice car. That's why most folks you see in movies and stuff like that in real life, you know, you get a nice new paycheck. Your first thought is to go buy a new Tesla, a new Lamborghini. Those are the kind of ideas you start seeing, especially for males. So you see that same kind of trend throughout the different age ranges. So this kind of shows you like, hey, salary times gender, there's something going on there. So we're justifying those interaction terms. Now let's talk about log terms. We tried adding log terms, but we're going to have 2 points on this. It gave us a better AIC than our interaction model 2, but it barely gave us that little inch of, just 1 unit of better AIC. So we went ahead and if we added that kind of log term, it's going to make our model even more complex to interpret. So we went ahead and said, okay, maybe we shouldn't add log as a team. And so we decided just keep it not too complicated enough. We're going to just add that. We're not going to add the log on the age and salary. And we're going to continue to work on interaction model 2, which we're going to build upon by adding more polynomial terms. So now let's see if we need to add a polynomial term. So if we look, so there's 2 predictors that we want to look at, which is going to be age and annual salary. And we have gender to describe both of them as well. And so if you look at the left model, the left graph, you see that, you know, as you grow in age for both male and female, you're more likely going to buy a car, which makes more sense. We use a higher span because if we use a lower span, it looked like a little dip. We went ahead and just pulled out on a higher span to make it look very nice and smooth. On the right side, though, you see that based on Blue's EDA analysis of having a little gap between, around 70,000 or 60 to 70,000 gap, there's going to be a little dip there that creates such a quadratic graph for annual salary match against gender. And so with that being said, we see that kind of quadratic movement parabola. We're going to go ahead and add a polynomial term to quadratic on the annual salary. And so we went ahead and did that. So we went ahead and just had the polynomial terms, which is just age, gender, and annual salary, which is 646. Which is for AIC is 646. And however, something interesting happened. The Haslam test showed that it rejected the null, meaning that it has a lack of fit. We went ahead and added interactions term to see what the AIC is. It was 595. And it still rejected the null hypothesis, meaning that it still had a lack of fit, even though we added polynomial term, interaction term to our model. And we went ahead and just added log term to see what would happen. The AIC actually got worse at 600, and it still rejected null hypothesis, meaning that we still had a lack of fit. So looking at this, you see that our complex model, even though it has a lot of terms with age, annual salary, the categorical variables, interactions, and the polynomial terms, it still had a good AI, somewhat of a good AIC. We still can't judge everything based on the AIC, but the Haslam test kind of was the final thing that said, hey, this shows a lot of lack of fit. Which makes sense, right? When you're thinking about buying a car, there's more factors, just age, annual salary, gender. There could be a lot of different things based on maybe race, maybe certain preferences based on, demographics and such things like that. Now what we're going to do is go into our, the other three models, which is going to be the GLMNET, which is our feature selection based on the log loss model metric. We went ahead and see which predictors are going to be remaining and which ones are going to be moved. And we used our feature selection model. We saw that gender and age range got removed and everything else stayed. So when we did that, we ran through the ROC curve, and our AU ROC is about 0.9566. So again, the reason why we're using GLMNET feature selection here is once we had a complex model that had multiple predictors, now we can see which predictors are significant. We're going to run it through the GLMNET to see which ones got removed. So we got removed gender and age range. Now we're going to talk about the QDA model. Our QDA model had the predictors age, gender, and annual salary. And based on Blue's EDA analysis, we saw that if you graph age against annual salary, you see that more points are at the bottom left of the model, which kind of creates a situation where we can classify the boundary using a QDA as opposed to LDA. QDA has more of a flow, more of a parabola kind of curve that kind of captures all the data in more classifications. And when we run the ROC curve, we got 0.9552. Now, with the same kind of idea, same kind of graph, we're going to try KNN, and our predictors is going to be our complex model predictors, which had all the same predictors of the interaction term, the polynomial terms, and the categorical and continuous variables. And you see that using KNN with drawing the circles, it seems somewhat you can use KNN just to make a good classification, but we're not sure yet. We'll see at the very end if KNN versus QDA would be better. The AU ROC is 0.8896. All right, so we went ahead and just applied all the ROC curves, see which one's the best. So we got 5 different ones: the base one, the complex one, the GLMNET, which have the removed predictors, QDA, and the KNN. Based on the output here, we see that the best AU ROC is the complex with 0.9655. Coming in second is QDA, 0.9552. But remember, the one thing about this complex is that it failed the Haslam test, which shows that it has a lack of fit. So again, pretty interesting stuff. The lowest one is actually KNN. Now we're going to compare our final models. So we're going to compare 5 final models, which is base model, complex model, GLMNET, QDA, and KNN. What we saw here is that they roughly have the same kind of statistics, with complex sort of coming in first technically, with a higher AU ROC. It has the highest sensitivity, second highest specificity, the lowest PBV, or the second highest PBV, and the third lowest NPV as well. Seems well, and remember, it had a lack of fit in the Haslam test. As a team, we decided to go ahead and go with the QDA. It had basically the best of everything. In terms of accuracy, it has good accuracy compared to the complex model, even though it has a lower sensitivity to the complex model and the GLMNET model. We're going to focus primarily on the specificity and the PPV, which is extraordinarily better, which is about 0.984 and 0.987. The AU ROC is not bad. It's only like one number off from the complex model, but still shows better performance in the KNN and the GLMNET. So our QDA is technically our suggested model. And so again, just as final remarks, technical winner here is complex with the A. If we're saying AU ROC is our final metric, it's a technical winner, but we're saying, hey, even based on that metric, it failed the Hansen test, and we aren't caring about sensitivity as much. We're caring about specificity, and it had multiple predictors, had 7 predictors as well. Our suggested model, if we had to go with any model, would be the QDA. QDA had an AUROC of 0.9655, specificity of 0.984, and only had 3 predictors. Okay. Now we're going to address the confusion matrix. Remember, our confusion matrix was our secondary metric that we're going to focus on. We're going to focus on 2 of them, which is specificity and PPV. So when you're buying a car, it's important to focus on what's the missing negative cases of buying a car, right? When you're like, what's not working in terms of buying a car, right? You're looking for opportunities or marketing purposes or identifying business opportunities and understanding why people aren't buying more. You're not understanding why are people buying cars, but you're saying, let's do some stuff to buy more cars. So we have to put more money on marketing, advertisement, making cars better, following new trends of, EVs, Teslas and stuff like that. It is important for a car company to use this data set for the purpose of training a model to find good predictors and seeing what makes people buy a car. So we also identify PPV because it helps us identify marketing strategies. Say, oh, is age, annual salary, and gender good predictors in finding, certain populations that we're going to target in terms of making more advertisement for them, especially for males, right? At a certain age, at a certain, salary range, people that are having more income at an older age and that are a male, maybe we should target them for marketing strategies and stuff like that for them to buy more cars. And now I'll make the final conclusion. So just again, do a quick summary conclusion of what happened. So we had on objective 1, we had a multiple logistic regression. We called it the base that had the variable age, annual salary, and gender, where age and annual salary were continuous, gender was categorical. Had AIC about 750, specificity of 0.602, PPV of 0.77, and AUROC of 0.91. Objective 2, we went ahead and created a complex model. We went ahead and made a GLMNET feature selection on those complex models, performed QDA and KNN based on our EDA analysis, non-parametric models. And if we compare base with the one that we chose was QDA, we see that we're not going to focus on the AIC. The log loss was about 0.308. Specificity was about 0.984. PPV was 0.9870. AUROC is 0.9585. So it was much better than our base model that we picked at first. A couple of things about this is the scope of inference. This is an observational study. So we're just collecting, 1,000 observations, no random assignment or sample. If we want to increase our effectiveness of our model, we might want to collect more data, not just 1,000 observations, and as well as possibly adding new predictors, right? There's more things that come into buying a car than just your gender, age, and salary, right? Be a lot of demographic situations such as race, where you live, things that kind of, motivate people to buy certain cars, right? So that concludes our presentation. Thank you so much for watching our video. If you have any questions, please contact us. This is my information, Jasmine's information, and Robert's information. Thank you so much and have a great day.